Hola Enrique.
Hola, ¿qué tal? ¿Pasaste ya el link a los señores de Ventú?
Sí,
Aún no lo han subido.
Bonjour, ça va?
Yo,
¿Qué tal?
bien, aquí estamos. A ver si acaban de conectar el link de YouTube a la plataforma.
¿Live en YouTube ahora mismo?
No, ahora no está en live aún, porque no está puesto.
Se me oye bien, ¿no?
Sí, prueba de compartir pantalla.
Vale, vamos a compartir esto. ¿La presentación se ve ahora?
Sí, se ve bien.
Estoy pasando diapositivas. Se ve lo que hago, ¿no?
Mm.
Vale, si doy escape se ve aquí todo esto, ¿no?
Sí, se está viendo aquí lo que es el PowerPoint tuyo.
Stop share. Uy, ahora te has cambiado el micrófono.
Sí, es que tenía los cascos puestos, pero estaba por el altavoz, entonces era un poco absurdo.
Yo me he traído también los cascos porque es que creo que se oye con mucho eco si utilizo el micrófono del portátil.
Hmm.
Tío, estoy haciendo la plenaria y estoy teniendo solo el trabajo de la plenaria, pero no me estoy llevando ni la invitación a cenar, ni el hotel, el viaje.
Es lo que tienes congresos online.
Esto está muy descompensado, Enrique.
Ya.
Esto no me sale a cuenta. Ay, señor. He visto poquísimo del congreso.
Ya.
Porque he estado muy liado con esto. ¿Qué tal os ha salido bien? He visto que había algunos problemillas con la plataforma.
Sí, hubo ayer unos problemas. Tienes que saber que todo lo que estás diciendo ahora se reproduce en directo.
De acuerdo.
Sí, hubo unos pequeños problemas ayer, porque se cayó la plataforma de Jitsi y bueno, al final nos dieron una salida entre los de Nunsis, que se portaron muy bien, que están aquí presentes, pero es cierto, hay que agradecer todo el esfuerzo que hicieron. Y los de Ventú también al final pues dieron una salida que sustituyeron la aplicación por otra y bueno, al final ayer por la tarde funcionó bien y esta mañana ha funcionado bien. Cosas del
Yo,
directo.
sí.
Se cae la plataforma y ¿qué puedes hacer? Nada.
El miércoles estaba bien la aplicación.
Sí, la
Te metes
aplicación
en la
estaba muy
web y
bien.
tal.
Sí. Y la de ahora también es más o menos lo mismo. Pero claro, tampoco puedes prever que alguna persona pues tenga algunos problemas para compartir la pantalla o cosas de ese estilo o a alguien se le corte internet. Bueno, esas cosas, pero claro, prever que se te caiga Jitsi es como prever que se te va a ir la luz en un congreso.
Ya.
Pero bueno, bien, más o menos lo pudimos salvar y realmente se dieron todas las charlas. Un poco de retraso por la mañana, pero bueno. Un poco de retraso
Eh,
fue 15-20 minutos, que tampoco fue nada exagerado.
ya. Oye, al final, ¿Dijiste a la mini sesión que me tocaba ir que no iba a ir? O...
Te quité de la lista.
Ah, vale,
Así que como no te vio, pues no te llamo.
bien. Es que no entré.
Hmm.
Empiezo sin compartir pantalla y luego cuando Santi me da paso, comparto pantalla.
Como te diga Santi. Él es el que manda de ti.
Es el que va. Y él me presenta.
Sí, él te va a presentar. Esa es la idea. Y también gestionar las preguntas, porque tú no las vas a ver.
Exacto, yo no tengo que abrir nada. Yo
No.
simplemente hago la presentación y ya me cuenta él.
Sí, a ver, las podrías abrir tú, pero bueno, él va a tener la plataforma abierta y esto abierto, y entonces él va a leerte las preguntas. Esa es un poco la idea.
Bien.
Yo cuando es interesante y más o menos esto funcione me saldré. Y me pondré solo a veros lo guapos que sois.
Sí, guapísimos. Bueno, ya está, ¿no? Ya se termina. Luego tienes que hablar tú, ¿no?
Sí, después queda la mesa redonda y la
Ah, no,
closing,
claro.
que se
Paramos a
hace,
comer y
sí,
mesa redonda.
y mesa redonda. Y la closing todo eso se hace con una reunión de Zoom todos juntos, para que la gente pueda intervenir fácilmente.
Como hicisteis la bienvenida, ¿no?
No, como eran los workshops.
Ah, vale, vale. Vais a dar un... Vale. Perfecto.
La bienvenida era como esto, era así.
Sí, exacto.
Esto queda mucho mejor porque queda embebido en lo que es la aplicación del Congreso,
Mm.
queda más formal.
¿Lo estáis
Pero bueno.
guardando?
Creo que sí. Carlos, se está grabando, ¿verdad? ¿En algún momento empiezas a grabar? No me estoy oyendo. Sí, en principio se está guardando. Creo que lo tiene Fanny, el del CCP.
Perdona, Enrique.
Nada, tranquilo.
Cuando comenzáis sí que empiezo a grabar, lo que pasa es que
Vale.
está planificado a las 12, ¿no? Entiendo.
Sí,
Sí,
sí, no
sí,
te
sí, sí,
preocupes.
sí,
Estamos
sí, es a
charlando,
las
estamos
12, a las
charlando.
12, no hay ningún problema.
Vale, vale, vale.
No, es que me lo han preguntado, ¿lo estáis grabando? Y yo creo que sí que lo graban.
No, ahora estamos en emisión y grabo la parte, digamos, que ya estáis en directo, por llamarlo de
Sí.
alguna manera.
Y está colgado en la plataforma el
Sí,
link.
de hecho, David me acaba de escribir que nos está viendo.
Mm.
Un saludo personalizado a David Muñoz.
Hola, Santi. Y está colgado en la plataforma.
Sí, de hecho, David me acaba de escribir que nos está viendo. Santi está mirando el vídeo diferido.
Sí.
Hey, ¿me oís?
Sí, te vimos. Tened en cuenta que todo lo que decís queda grabado. Bueno, queda grabado no. Queda
Está
grabado
emitiendo.
en la retina de los.
Estamos retransmitiendo.
Sí,
¿Ah,
estamos
sí?
retransmitiendo en
Ahora
directo, eso
sí.
sí. Sí. Sí, cuidado que no hay micro off, que no hay micro off.
Vale, no puedo insultar a nadie.
Bueno, a mí si quieres sí.
Se me ve
Ay.
oscuro, se me ve oscuro, ¿no?
Sí, hay una
Un
opción
poco,
en
sí.
Zoom. Si te falta luz, hay una opción en Zoom para que te suba la luz. Yo lo he puesto.
¿Dónde está?
Pues a ver, vas a opciones del Zoom y en vídeo.
Espera, que tengo que encontrar primero opciones del Zoom.
No, claro, yo es que estoy con el Mac. La ruedita.
En el desplegable de abajo a la izquierda, donde tienes el micrófono y el
Sí.
Ah,
vídeo,
también, ahí también,
Sí.
exacto.
ahí hay una
Eh,
flechita que te redirige hacia la configuración.
Video settings.
Configuración de audio y configuración del vídeo. Vale.
Y yo tengo una opción que es Adjust for Low Light. ¿Ves? Y te da un poquito de brillo.
Ole, canasta.
Ajustar para poca iluminación. Vale. Sí, mejor.
Yo también lo tengo puesto porque aquí está nubladísimo. Llevamos 3 semanas, Santi, que no pasamos de 23 grados.
Ostras.
Qué bien, ¿no?
A ver,
Llevamos semanas que no bajamos de 23.
espera, voy a salir y vuelvo a entrar, que se me ha...
Efectivamente. Es una sensación extraña porque a principios de junio, estuve una semana en Valencia y ya había clima de verano. Y he vuelto aquí y no parece que sea verano.
Vale, ahora. Aquí para el lunes dan 40 grados.
Sí, para el domingo también. La puse a casita y a remojo.
Es lo que hay. Santi, ¿qué hago? ¿Comparto la pantalla desde el principio? ¿La comparto cuando tú me digas?
Pues compártela desde el... No sé, ¿cómo lo han hecho los otros, Enrique?
Yo creo que la compartía desde el principio porque pues, vuestras caras creo que se ven.
Sí, al ladito se ven, ¿no?
Sí,
Vale,
Entonces lo dejo así.
déjala así.
Sí.
Perfecto.
Ya lo puedo ir pasando yo. Sí.
Va todo bien, ¿no? Y tu puntero se ve también si lo mueves, ¿no? Sí. La barriga del avión.
La barriguita.
¿Tiene algún nombre específico esa parte?
Bark Central. Es como la llaman ellos.
panceta. Panceta.
¿Bank o bark?
Bark.
Bark, de barca.
Sí.
Se llama panceta.
Pero vamos, no creo que tenga Bark Central y también hemos hecho cosas con la Bark lateral, que es este de aquí.
Ujú.
Ahora siempre lo miro cuando voy al avión, me fijo.
Normal.
Santi, prepárate preguntas.
Ya están preparadas.
Vale.
A ver, las preguntas la gente las escribe...
En el chat, si tú tienes que tener oberta la plataforma también. Y verás
Ah,
el
vale,
chat.
això anava a preguntar-te. On veig jo les preguntes?
En la plataforma. Lo abres y les verás que un van y después les diriges a José Manuel.
Vale, d'acord. Vale, questions may be sent on... hasta les 11 menys 10, 12 menys 10 no deixa.
¿Quieres saludar a José Manuel? Espera, que te cambio el audio y lo saluda.
Ah, estàs dalt, no, Enrique? Sí.
Sí.
¿Cómo es que el otro día no me lo dijo? Que...
Pero dile que está en emisión.
Ah, estás en emisión en directo, ¿eh?
Saluda, Manolo.
No, te preguntaba que como el otro día no me dijiste que ibas a hacer la plenaria.
Sí, es que no lo sabía, Manolo. Por eso no te lo dije.
Sí. Pero no deberíamos hablar en inglés. No, empezar entonces. Esto es como está en emisión. La charla previa. Sí. Entonces te enteraste hace poco, tú también.
Sí.
Desde aquí se está reproduciendo ya. Van en un poquito de lag, pero sale. Por eso no te lo dije. A ver, ¿y qué, de qué vas a hablar?
Combining Shape Statistical Models and Reinforcement Learning.
De lo que...
El proyecto que he hecho aquí.
Enrique, pero yo en la plataforma no puedo ver el vídeo.
¿Quién eres tú? ¿Santi o...?
Santi,
Sí, sí que puedes verlo. Lo que pasa es que lo ves con un poquito de lag.
pero no me sale.
Sí que sale, yo lo estoy viendo.
Bueno, a mí no me está saliendo. Me dice expand vídeo y no se ve el cuadradito con el vídeo.
Actualiza la página.
A ver.
Voy a por agua, ahora vengo.
No me sale, ¿no? Ahora.
Good luck, Mr. Navarro.
Ya está, ya me sale, sí.
Ten minutes. Me están diciendo que se nos entiende muy bien en castellano y valenciano.
Hombre, la verdad es que la sesión del otro día de trenes yo estuve a punto de hacerlo todo en valenciano.
Ya. Carlos,
Dime, Enrique.
sí, para la mesa redonda de esta tarde, lo que empieza a las 2:30, entramos como los workshops a través de la plataforma, pinchamos y entramos ya y nos
Sí,
enlaza con
el,
el
for-
link a la sesión de Zoom todos juntos y ya está, ¿cierto?
el formato reunión, sí.
Vale, gracias.
No los workshops.
Es para enviarles un correo a los participantes de la roundtable para que lo sepan.
Quizá que lo diga Santi al final de esta sesión o qué.
Sí.
¿Qué
No,
queréis que
la
diga?
gente lo sabe, simplemente le envío un correo a los ponentes de la roundtable.
Que,
Ah,
que la sesión, que la siguiente sesión es a través de una reunión de Zoom directamente. Que
pero,
en la,
pero la gente, ¿dónde tiene que entrar?
a la aplicación, a la
En la
sesión y eso les
aplicación hay un
enlazará.
link a Zoom.
Ah, vale, vale.
Nada, simplemente entran ahí, ven un link y entran. Ya está. Como en los workshops. No sé si fuiste.
Sí, vale.
Bueno, chicos, yo creo que os voy a dejar. Al parecer aquí todo está en orden. Si hay alguna cosa, me escribís por el WhatsApp o por el que sea, ¿vale?
Vale, Enrique, de acuerdo.
Venga, hasta luego.
Chao.
Chao.
Chao. Tú eres el plenario más joven, ¿no?
Eso parece.
Vale.
Vas a remarcarlo.
So let's wait 3 minutes more. Well, it's 12 o'clock. We are just in time. So welcome everybody to this last plenary talk of the conference. My name is Santiago Gregori. I'm assistant professor at Polytechnical University of Valencia. And well, we are here in a young investigators conference. So I have the very pleasure of presenting you, of introducing you, the youngest plenary speaker of the Congress. He is Jose Manuel Navarro. He obtained his PhD in 2019 in computational contact mechanics. During the PhD research, he made a stage at the Sienkiewicz Center for Computational Engineering at Swansea University under the supervision of Professor Ruben Sevilla. Since that year, he's postdoctoral researcher at Institut de Càlcul Intensif at École Centrale de Nantes in France. And in this plenary lecture, Jose Manuel will enjoy us with the very interesting work he and his supervisors and colleagues have made during these 2 years of postdoc. So, Jose Manuel, if you are ready, it's time to hear you, and the floor is yours.
Yeah, thank you very much, Santi. I have to say that I think that also we have the youngest chairman, right? If I'm not wrong. Well, hello everyone. It's my pleasure to be here as a plenary speaker in this very nice conference. I want to thank the organizer and especially Enrique Nadal, who contacted me for this. And also it's a shame that we're not able to be there in presence. I mean, the UPV is my home university, so I would have enjoyed very much being there and seeing again familiar faces and also knowing other very interesting people for sure. But the situation is as it is, and we have to deal with it, right? Well, I'm going to talk here, as Santi said, about my work during my postdoc here at Institut de Càlcul Intensif in École Centrale de Nantes in France. And this is done in collaboration with my colleagues, José Vicente Aguado and Domenico Borzacchiello, and also with Grégoire Bassin, which has been our link with an industrial partner that we have in our project, and it's Stelia Aerospace. So let me start by introducing you the application case that we had, and this will better illustrate the problem that we are facing. So Stelia is a manufacturing company in the aeronautical sector, and they produce aircraft components, and in particular they're interested in improving the manufacturing process, the productivity of the aluminum panels that form the aircraft fuselage, like this one that is depicted in this photograph. So these are quite big panels. There are pieces that are more than 6 meters long and 2 meters wide. They go through a metal forming process first to give the pieces the desired curvature. And after that, there is a high precision machining process in which they are much interested in reducing the thickness of the panel at specific regions. So consider that these holes that you see in this picture are not actually holes, but these are the regions in which they want to reduce the thickness of the panel in order to reduce the weight of the aircraft in the end. So although these are big pieces of metal, as I said, they are quite thin, only a few millimeters of thickness. So they need to have a very high precision workshop for machining this component. And they also need to include a digitalization of each of the pieces that they produce. And why that? This is because after the forming of the metal sheet, there are some differences with respect to the design CAD shape. And these differences are small, but are within the tolerances of the quality controls that they have. So they need to scan, as I said, each panel one by one with a laser scan, and then they can adapt the machining trajectories that were designed in the theoretical CAD, let's say, and they adapt it to the real shape of the geometry. This is considered to be a non-productive step in the production workflow, and we were interested in reducing the time that is spent in identifying the shape of the panels. So the main question that we face is this one. So can we identify a shape with high precision? But using an incomplete digitization, we want to avoid a full scan of our shape. Well, we think that if we can build a parametric model that captures all the variability of my family of shapes, then we might be able to take only an incomplete sample of a new incoming shape, identify it in our parametric shape model, and then we reconstruct and have the reproduction of the actual shape of the panel. So this leads to two different tasks. In first place, I need to build a parametric model of my shape. I am sure most of you deal almost on a daily basis with parametrizations, like, for example, CAD geometries or finite element models, or even reduced order models built upon finite element models or CADs. The problem here is the raw input that we have is just a point cloud and nothing else. So we have taken the ideas from the computer vision and medical imaging communities, and we are going to explore the statistical shape models that I will show you later. Then, after having the parametric model, we need an incomplete measure strategy. How do we partially scan our panel? Well, in first place, we looked for the simplest solution, which was trial and error, and we tried with some arbitrary trajectories. But after that, we thought, well, maybe we can set this as an optimization problem. I have my parametric model and I want to sample it with the minimum amount of data possible. And as we had set our problem, we thought that reinforcement learning was an interesting approach to solve it. And I also will show you how we did it. So the presentation is split into two parts, each one regarding one of the concepts I depicted before. First, I will show you the methodology that we have developed to reconstruct a shape from incomplete data. And in the second part, I will show you how we try to obtain optimal measurement strategies using reinforcement learning. So let's start with the first part. There are different steps. First, we have to build our statistical shape model. Then I will show you some metrics that assess the quality of that model that we built. After that, the shape reconstruction algorithm from an incomplete data. And in this part, this incomplete scan will be a fixed arbitrary trajectory. And I will finish the first part by showing a test that we did in situ at Stelia's workshop. So this is the method overview, and let's start by creating the statistical shape model. For that, we need a database of complete data. Luckily at Stelia, they had saved the scans of lots of panels during the last years, and they provided us with a database of 555 panels. And with that, we try to build our parametrization. And the statistical shape model building is divided in 3 steps. First, the alignment of the shapes, then registration, and finally the dimension reduction to obtain our low rank approximation of the variability in the model. And now I will detail all those 3 steps, starting by the alignment. Well, there are iterative methods that try to find the objective here is to reduce all the rigid body motions that might be with respect to the different samples in the database. Take into consideration that these scans might have a different reference system, so we have to align them first in order to extract the variability. As I said, there are iterative algorithms like the iterative close point algorithm that try to do this in a recursive way. But here we took advantage of one feature they already had at Stelia, and is that they have 2 reference landmarks. There are 2 very small holes that are located near the boundaries of the panels, and they use this reference precisely to locate the panels in the coordinate system. So what we do is for each sample in the database, we make a translation so that the first landmark phi1 is located at the center of our reference system. And then we make rotations such that the line that connects both landmarks coincides with the x-axis. So now we have reduced all the rigid body motions, and it's time to make the registration. This works as follows. First, we have to choose a template shape. This choice is also arbitrary. We have chosen this rectangular mesh that is that has more or less the same dimension of the panels in the database. And now the objective is to find a mapping of the template such that it fits each of the samples in the database. For example, we here want to obtain mapping A1 such that we deform the template shape and it fits the first shape in the database, and so on for all the 555 panels. How do we do this? Well, the shape statistical models, and in particular the point distribution models, which is what we are concerning here, need some correspondences to be established between the shape that we are registering and the template that we define. Think of medical imaging segmentation, for example. When we select the specific features of the bone or of the tissue that we want to extract from the image, we are establishing that correspondence manually. Here we can use as those landmarks the boundary and the corners of our shape, which luckily can be almost automatically detected. We know that the shape is going to be a rectangle, and we can extract the boundary and the corners. However, that information is not enough, because we will be missing all the curvature that is inside the panel. For this reason, we split the registration into two phases. On the first phase, we will register the plane coordinates, the XY coordinates, following the scheme that is depicted in this picture. So we set that the perimeter of my template shape must be mapped onto the perimeter of the shape that we are registering. And to obtain the deformation of the bulk of the template shape, we use the thin plate spline, which is minimizing the energy bending of this mesh. Now that we have the mapping on the plane coordinates for the template shape, we need to extract the information of the out of plane coordinates. And we do that with a weighted average of all the points in the sample that are in the neighborhood of a given node in the mesh, and using a Gaussian filter. So we do this weighted average for each node in the template mesh, and we obtain the coordinate, the out of plane coordinate for all the nodes in the template. With this, we have the mapping of the three-dimensional coordinates of my samples in the database. Having that, the rest is a standard procedure that any of you that has worked in reduced order model will be familiar with. So you can understand the registration of each shape in the database as snapshots of my environment, of my environment that I want to reduce its dimension. So I will gather all the registration of the samples in the database in matrix A, then compute the mean shape and subtract it from the matrix. And then I will apply the SVD to that matrix with the variability. And the statistical shape model definition is the combination of the mean shape plus the variability, which is expressed in a compact way with the modes and its shape parameters. And here you have in these pictures two of the most important modes with the variability of the panels in the database. So now that we have created our statistical shape model, we're interested in knowing and assessing the quality of the model, if we can use this for our industrial case. For that, we took three different metrics that are used widely used for statistical shape models, which are the compactness, generalization, and specificity. The compactness is the cumulative value of the singular values associated to the modes of my reduced model. Then the generalization measures the ability of the model to represent any shape that hasn't been yet seen by the model. So it measures if I can represent accurately any sample that is outside the training set. And finally, the specificity measures if the span of the all possible geometries that my statistical shape model can generate is close enough to the training data. So if my model only spans feasible shapes and it's not generating other shapes that are not resembling a panel. So I show you here these metrics computed for our model. You can see in first place that the model shows some compactness. So after 50 modes, the influence of the following modes is significantly reduced. Then the specificity also reaches a constant value when the number of modes is increased, and this is good. This is what we desire, and that means that the span of our model is bounded and it is close to the real span of possible shapes that might be. And finally, if we see the generalization graph, we see that we reach a precision of nearly 0.04 millimeters. This is the average distance between a panel that was outside the training set and its projection on the statistical shape model. This means we can represent any panel with less than 0.1 millimeter accuracy. And it is quite good for us, taking into consideration that panels are several meters long. And also another thing that I didn't tell in the beginning is that the file in which the point cloud comes in has a numerical precision of 10 to the power of -3 millimeters, meaning that we are almost 1.5, let's say, order of magnitudes above. So we are quite close to the numerical precision. In light of these results, we thought that we could use a truncated basis with 100 modes, and this way we increase the efficiency of the method, but we still keep the highest accuracy in which we can represent any panel. So now let's see how can we identify a new sample that comes not with a complete scan, but with a partial scan. As I said in this part, we will use the partial trajectory that is depicted in this figure, and we chose this arbitrarily, and it was designed with the help of the technicians at Stelia, and also considering the technical constraints that their device had. So now we have as an input a point cloud that is only the blue part of this panel with points with xt coordinates. We also have the same landmark locations as we had for the samples in the database. So we make in first place the alignment of this partial measure. And now we need to identify the shape parameters of the model that correspond to this new shape. For this, we solve a fitting problem in which we reduce the distance between the interpolation of the statistical shape model in the partial measure points and the coordinates of those partial measure points, where we use standard finite element interpolators to make that interpolation. However, this is a nonlinear problem because in order to interpolate the statistical shape model on the partial measure points, we need to know its location on the template shape. This is the same as when we are trying to locate a point in the space in the local reference space of a finite element, right? We set a fixed point algorithm to solve this nonlinear problem, and we found that we had convergence in 10, 15 iterations, which in practice was good, and the results were satisfying for us. So after we have identified the shape parameters, we have one more step, which is a panel reconstruction, the oversampling step, we call it. So first, when we were creating the statistical shape model, we saved a reconstruction point cloud so that we have a cloud with the same density as that of a complete scan. And now we have this new panel that we have scanned partially, and we have identified the shape parameters. So it only remains to interpolate with my shape parameters on the reconstruction point cloud, and we will obtain a new point cloud with the complete description of the geometry that came lastly. With that, we have a method that is non-intrusive in the sense that if you see here again the workflow at the manufacturing plant, instead of making a complete scan and having that point cloud and then adapting the machining trajectories, we will now make a partial scan, the shape reconstruction, and we provide a similar point cloud that can be directly introduced again in the data post-processing algorithms that they have at the manufacturing plant. We have tested this at Stelia's workshop, and we did 9 different tests with panels that were in the production line, and they were scanned both completely and partially to check if we were making good reconstructions. You can see here the plot of the reconstruction error, which is the distance between the complete scan and the reconstruction that we provided. And we see that the average error is near to the generalization ability of the statistical shape models, meaning that this nonlinear problem, fitting problem that we are solving is not introducing much error. We saw that the reconstruction error was suitable, and then the adaptation of the machining trajectories was performed using the reconstruction file that our method provided. Then those panels were machined and they successfully passed the quality tests. So in the end, we estimate that with this methodology, when we can reduce the time spent in this digitization procedure by an 80%, which is quite a good result. And last, I will like to draw your attention. Maybe you have noticed that there is one panel that has almost double the error, and the number 6 reference. It has an average error of 0.1 millimeters. And you can see that there's something weird in the error plot. And if we make a zoom and if we focus on that reference, I guess that you can clearly see that there is a pattern here. So there are the error is higher in some vertical stripes that are distributed along the panel. So we examined in depth this panel and the inputs that we had from the panel, and eventually we detected that there was an anomaly in the digitization process. So we could say that the complete scan that came to us was corrupted. And we were able to detect this thanks to the statistical shape model. We detected here some problem. So let me conclude this first part by saying that I presented you the methodology for fast 3D surface reconstruction that combines a parametric model of the surface and partial sampling of the following shapes. For the statistical shape model, we use as only landmark the boundary, which can be automatically detected, but we need a 2-step registration method in order to take into account the curvature inside the panels. Then the statistical shape model proved to have a high accuracy that fitted the quality standards that we required. And we designed a nonlinear fitting problem to reconstruct, to identify the parameters, the shape parameters of a sample that comes with a partial sampling. And with an arbitrarily chosen trajectory, we were able to provide good quality reconstructions, achieving estimated time reductions of 80%. And this late idea that we haven't explored in depth is that we think that we could detect anomalies in any aspect of the previous workflow, in the workflow previous to the digitization process, thanks to the statistical shape method property, the statistical shape model properties. Sorry. So now let's go into the second part, which is focused on that measure strategy, how to obtain an optimal measure strategy, in the sense that we want to have the less data as possible, because the less data we acquire, the fastest it is. For that, we thought that reinforcement learning was promising, and I'm going to show you a bit the basics, because I think that in our community, well, for sure, machine learning is a trending topic in our community, and I would say in any community. But I think that we, at least when I started this project, if I thought about machine learning, in my mind, these kinds of images appeared. So we usually think about, we have an algorithm, and we are trying to that this algorithm extract features in that data, in the data that we fill the agent with. These features might be hidden. We might not know which are these features, or maybe they are known, as here in this example. For example, I know this is a 0, and I want my agent to detect that this is a 0. So, and this is because then I want to give that agent another image in the future, and the agent will be able to predict what number is that image, right? But reinforcement learning paradigm works in a different way. In reinforcement learning, the agent interacts with the environment, and those interactions affect the final output. I think, for example, in a game of chess, the agent, the reinforcement learning agent, plays the game, and its actions, its movements, its plays will affect the final result, which will be, in the end, I have won the game, I have lost, or I have drawn the game. You can also think about any other process that is sequential and it has variable input, and those inputs have affect the final result. For example, a polymer curing process, where you might have a variable temperature and pressure, and those values of temperature and pressure will affect the final properties of the polymer or the curing speed. Then also, I have read recently another paper that explores reinforcement learning for age-adaptive finite element meshes, in the sense that you have a sequence of meshes, and you have to decide which elements to refine in order to minimize the error with the less amount of degrees of freedom as possible. So you can think of any of these processes. Now I'm going to briefly show you the basics of the theoretical basis of the reinforcement learning, which goes back to the Markov decision processes back in the 1950s. First of all, we have to define the state of the environment. This set of variables that give all the information that the agent needs to make the decisions that it has to make. And it is important that the state includes information about all aspects of the past interaction between the agent and the environment. This is because at a given time step, the agent will only know the current state, and the agent won't know all the previous states he was in. Then the agent we will allow the agent to interact with the environment with a set of variables that can be arbitrarily changed, and those are the actions. Anything else is internal to the environment, and the agent will know nothing, as in a black box. Lastly, after each interaction between the agent and the environment must output a reward, and that reward is given at each time step and must be directly linked with the goal we want to achieve and as unbiased as possible. For example, if we are playing a game, the reward should be only the score of the game, or whether if I have won or lost the game, but nothing else. Maybe there is one action that we a priori know it is good, but we should not give any of these informations in the reward to the agent. He has to discover all of that. The objective of the agent is to maximize not the instant reward, not the reward at that time step, but the cumulative reward. So this is also called the return, and it is expressed as the instant reward, the reward that I'm giving after this interaction, and all the future rewards that I will have. These can conveniently be rewritten in a recursive form as the return at a given time step is the immediate reward plus the return of the following state. And with this form, we can also include the discount factor, which is a weighting factor that with this factor, we can modify the influence of the instant reward and the delayed reward. Now, just a couple more things to define. We say that we set the action value function as how good is for us to take a specific action A, when I'm at state S. So this is nothing but the expected return, that if I am at this situation and I act having action A, I will expect that return. The problem is that we don't know a priori the return, because the agent doesn't know any information about the environment in the beginning. If we knew the action value of all the possible action at all possible states in the environment, the way to act, the policy, would be straightforward. We would choose a greedy policy, meaning that at each state, we would look all the possible actions, we would look all the action values, and we would take the action that give us the best return, right? We can write this again as in a recursive way. So the action value at a given state and taking a given action is the immediate reward plus the best action value that I can get in the next state. The problem is, as I said, that we don't know how the environment, how the reward is distributed along the environment. We don't know a priori what is known as the dynamics of the Markov decision process, which can be mathematically formulated as this function P of 4 inputs. And it's the probability of being in state S, taking action A, and ending in a new state S prime with a reward R. If we knew this function P, we will be in another, we would use another thing called dynamic programming that I'm not going to enter. But as I said, we don't know, and it is the basis of reinforcement learning. And how do we compensate this lack of knowledge? By exploring the environment. So I'm going to show you now one of the different algorithms that are based on reinforcement learning, which is the Q-learning. And I think it's the most popular, and it's a simple one. So let's assume, we must assume in the first place that we have a discrete set of states and actions. This could also be extrapolated after to continuous variables, but for the sake of simplicity, we stay with discrete sets of states and actions. Now, if we build, now we can build this table, the Q table, and we would like to know the value, the action value of all combinations of states and actions. If we know that, it's just about following the maximum action value always. So how do we explore the space? Well, the agent will run episodes. The simulations are called episodes. And at each episode, we will start at an initial state. And now the policy will be epsilon greedy, meaning that in general, we will take the best action up to our knowledge. We must initialize this table with some values, maybe random values, and we will start choosing the best action that we know at the moment, but with an epsilon probability, we will choose a random value. With this policy, we ensure that we will keep exploring the state action space always. Then after choosing one action, we interact with the environment. This is, we take action A and we observe the output. We have a reward and we have a following state. With this information, state, action, reward, next state, we will update the action value that we have in the current place. And we do the update with this expression, which is similar to a gradient method, and we introduce the alpha parameter, which is the learning rate, and is similar to the step size on the gradient descent method, for example. After this interaction, we are in a new state, S prime, so we go again to that state, we look for the best action following the epsilon greedy policy, and we go on and on until the episode is finished. And the training consists of lots of episodes until the values when it converts is because the values in the table will stabilize, and then by following an epsilon greedy policy, we will maximize the reward that we are obtaining. So how does all of this apply in our problem? Back to our application case. So remember, we want to reconstruct our panel. We have already, in this part, we have already our parametric model, and we want to sample our panel with as less data as possible. So now the partial scan becomes a data input stream. We will be scanning the panel, and as we scan the panel, we will make the reconstructions until the reconstruction is good enough for us. So the reinforcement learning algorithm will have to move the scanning device, and we'll have to look for the optimal strategy to scan the panel to obtain a reconstruction in the minimum possible time. So we have to formulate our environment, and we have done it like this. So the state will include the current position of the virtual scanner, which is depicted here by this square, and it will be a discrete set of possible positions. The scanner will be allowed to move in between all the red points in this grid. Then, to be able to decide when the reconstruction is okay, we have divided the panel in 4 sectors. Only 4 sectors to keep the number of possible states in our bounded, let's say. And then for each of the sectors, we will evaluate the average reconstruction error, and we will include a logical value indicating if we pass or fail a given threshold of error. The possible actions are straightforward. The virtual scanner will be able to move 1 step aside to any of the surrounding points in the grid. And if you remember, we have to define the reward directly linked with the goal we want to achieve and with any bias. So we have defined a constant reward of -1 at each step. So each step that the scanner does, it will have a reward of -1. Why? Because it represents that time is being spent, time goes by. So the reinforcement learning algorithm will try to maximize the reward, and since this is a negative reward, he will try to achieve a proper reconstruction with the minimum steps possible. Finally, to give the algorithm a warm start to accelerate the convergence, we decided to first scan the boundary of the panel, and that the virtual scanner will always start at the initial position located in the bottom left corner. So here is a test we made in our office with an environment consisting of only 1 panel, meaning that the reinforcement learning agent is scanning the same panel every episode, and it's trying to find the optimal strategy to build a reconstruction of the panel. After some training, it reaches to this solution, and if we compare it with the arbitrary trajectory that we defined in the first part, we see that we have more or less the same accuracy. We put that as a constraint, and we need almost half the distance of the scan. This could be related to the time. So we could do this half the time that we spent with the arbitrary trajectory that we designed in the first part. But I'm showing you now this second test to illustrate that the converged solution of the reinforcement learning is not a particular path. The solution was not the path itself, but the whole scan strategy. So now in this environment, we have two different panels. At each episode, we feed the agent with a randomly chosen panel between both of them, but the agent doesn't know which panel is it. And the agent starts exploring the state space and interacting with the environment. So after training, we put panel number 1 to the agent, and we see that it needs this trajectory to obtain a proper reconstruction. The same agent, we now put the second panel into the agent, and it needs a bit longer scanning trajectory. So this is the training outcome of the reinforcement learning algorithm. It's not a particular trajectory, but it's the policy. The agent somehow knows what to do at any state that he is located. Finally, a note on the convergence of these algorithms, or more like a warning, I should say. I showed you here in the first graph, I'm showing you the convergence of the training, representing the average steps that the scan needs to achieve a good reconstruction. In blue with the Q-learning algorithm that I explained, and in red with a slightly modified algorithm, modification from the Q-learning algorithm, which is DINA. And you see that slight modifications in the algorithms can lead to very different convergence speeds. The convergence in these methods is ensured if you visit all state space pairs an infinite number of times. We don't have infinite time, for sure, when we are computing our algorithm. So we need to also explore the state space in a wise way, and there are quite a lot of methods to do that, and they are usually problem dependent. So it's a bit complicated to find what is your place given your specific problem. Also, the meta parameters of the reinforcement learning algorithms, the learning rate, the discount factor, and the epsilon greedy ratio will affect the convergence greatly. Again, this is usually a problem-specific issue. There might be some meta models to adjust the parameters, but in the end, as I have heard lots of times from Professor Paco Chinesta, we must fulfill the principle of conservation of difficulty. So we are solving a problem to solve our problem. We have reinforcement learning will find the solution for our problem, but for that we need to solve the problem of which parameters to use in the reinforcement learning algorithm. Finally, I will end my presentation by showing you the current work that we are doing. We learned a lot with that environment, with that simple environment that we created, and to use with Q-learning algorithms. But it's not complete enough, in the sense that we are not fulfilling the Markov property. This means that the agent only knows the current position of the scanner, but the agent doesn't know, with our current definition of the state, the agent doesn't know all the previous places that we have already scanned, all the history, all the trajectory. And that is quite relevant for the outcome of our environment. There is no sense in going again and again through the same spot because we acquired the data in the first place. Therefore, we would like to include the scan history in the state definition, and we would also like to have a better error measure instead of these 4 sectors. We want to have more richness to detect some special features, maybe. For that, we would need to increase dramatically the number of states and actions, and then Q tables and Q-learning algorithms are not suitable for that. And now neural networks come in, another trending topic. And then when you combine reinforcement learning with neural networks, it is called deep reinforcement learning. So the basics in a nutshell, the difference is we still want to calculate the action value function, but now we want to express it as a table. We will train a neural network and we will try that this neural network predicts for a given state which are the action values of all the possible actions. The rest of the algorithm is more or less similar to the algorithm that I showed you for Q-learning. So we have made a preliminary test, only changing the algorithm, but keeping our environment, keeping our simple environment. And here are the result. We made some tests with different neural network architectures. Again, regarding the parameters and the fitting, tuning the parameters, we now introduce the neural network. We have to choose an architecture of the neural network, and that is another problem also. But yeah, these with simple neural networks, we had more or less the same results, and we were happy with this. So we can go now and define more complex environments. So here is the way that we are going to define our environment now, and the state is going to be encoded in an RGB image. So this image will be the input of our neural network. Now we have all the information that we need to represent precisely the state of the scan. In the red channel, we will represent the scan's traveled path. So these are all the places where the scan has already been. In the green channel, we have the scan's current position. Now you see here the scan's position in yellow, because if you mix red and green in RGB, you get yellow. And in the blue channel, we have the panel reconstruction error, and the average is done now with the same discretization of the grid where the virtual scanner can move. So if we plot just the reconstruction error with the usual jet color map, this is the aspect of the reconstruction error at a given time. Now, maybe you expect more colorful images, but I'm sorry to say that this is where we are now, and I cannot show you anymore. We are working on having solutions. So let me conclude this second part by saying that that we think that reinforcement learning is a very interesting machine learning paradigm in all that concerns sequential processes in which you have to take decisions, and those decisions influence greatly the output. And also, if you have an environment that you can represent with a reduced number of variables, with a reduced number of states, tabular methods such as Q-learning are great. They are simple. You have lots of implementations already done on the internet. And we tried that, and we found that we can have optimal scan trajectories that are almost half the length than that one that we designed arbitrarily. Now, we're interested in a more complex environment such that we can fulfill the Markov property. So we are looking now into combining reinforcement learning with neural networks, which is called deep reinforcement learning. But this comes at the cost of longer trainings. We have to choose the neural network architecture, and we have maybe to increase also the computation efficiency of our algorithm to make thousands of simulations. And I want to finish by telling you our next idea that we are thinking of. And if you see in this work, I've presented you two different parts that were quite differentiated. First, we built the statistical shape model, and then we try to exploit that statistical shape model, like identifying shapes in my model with the minimum data possible. Our question is, can we design an artificial intelligence that manages both processes at the same time? Meaning that I will start likely scanning complete shapes. I'll start scanning lots of shapes, and the artificial intelligence algorithm starts building the statistical shape model, and he decides when is the appropriate moment to stop scanning completely and start reducing the amount of data that we need to identify our shape. That's the current thing that is occupying my mind. Well, so that's all from my part. I hope you enjoyed this talk. I want to acknowledge also the funding entities, and again the organizers for organizing this conference and for inviting me. Thank you very much.
Thank you, Jose Manuel, for this very good talk, which describes very impressive work with good and practical results. And now it's time for questions and discussion. We have 10 minutes. So I remember that you have the questions tab on the platform, so you can write on the questions you have, and I ask that questions to Jose Manuel. There is one question from Enrique Nadal. Well, he first says that many thanks for your nice presentation. And he asks you that are you using any regularization to reconstruct the surface?
Any regularization in what sense?
I don't know, Enrique, if you want to better specify your question.
Here, you mean any regularization of this term? No, actually, we're just minimizing we're using a least-square fitting for that. Do you think that maybe to regularize because the number of points might be so high? It's a thing that we didn't consider when designing this algorithm.
Okay, thank you for your answer. We have another question from Filippo Massi. He says, thank you for this very interesting presentation and work. Have you thought of using, instead of the entire past scan path history, a reduced version of it, using, for example, model order reduction approaches?
Well, the thing we are considering how to define this more complex environment. Yeah, this approach that we took is based on the developments that Google DeepMind made on the Atari games. They designed a reinforcement learning environment that could could play and win most of the Atari classical games that have very bad resolution. So you have a very coarse image. And then we thought that maybe we could also represent this as an image. And the idea is that we want to use convolutional neural networks as the neural network that will predict the action value in this environment. So we think that if we just draw the trajectory that we have traveled up to now, this idea that Filippo says that maybe considering a reduced model of the possible history would be a feature that the convolutional layers would extract from the image. Like we thought of giving just the raw input and letting the neural network extract the reduced model of the history. But yeah, probably it's also an interesting idea to just give the algorithm some task already done, because yeah, that would increase probably the convergence speed of the algorithm. It's an interesting approach. Yeah, thank you.
Okay, thank you for your answer. Yes, Enrique Nadal just says that yes, he meant for avoiding spurious behaviors, as you answered before. Yeah.
We didn't consider maybe it would be helpful, and maybe the fixed point algorithm would converge a bit faster. But in practice, we didn't have any problems, so we made that assumption that if anything is going well, you don't touch it, which usually works until it fails.
So I have one question regarding this fixed point strategy to solve this nonlinear fitting.
Yeah.
So I wonder if you have any specific strategy to make the initial guess, or if it's just for trial and error. I don't know. How do you deal with?
Yes, we have tried with two different initial guesses. The first one is straightforward, is starting with the zero solution. So we starting with the 0 solution means that we set all the shape parameters to 0, and this means that we are considering that the panel that we have is the same as the mean shape. And with that, we can do the first interpolation, and then we keep on. This worked, but it was the convergence varied from sample to sample. So we thought of another approximation, and we have another approach that is we can extract the boundary of this partial sample as well as we did in the registration for a complete sample. So we extract by extracting the boundary of this partial sampling. We can manually make the first mapping of only of those points in the boundary. And with that first iteration, we have an initial solution that is a bit better than considering the mean shape of the panel.
Value. Yeah.
The drawback is that you need to have a partial measure that goes to the boundary at some points, and that represents the boundary good enough.
I understand. Yes. Maybe another question now regarding the second part of your talk, because, well, you explained the Q-learning algorithm, but you make some notes about another maybe improved strategy you called DINA, I think. So what do these improvements consist on?
I thought of also explaining this algorithm, but I didn't have time enough, and I think it's better to keep it a bit simple and not throw you lots of ideas at the same time. But yeah, these DINA algorithms, and it's a branch, an evolution, let's say, of the Q-learning algorithms, are based on updating more times the action value function as we interact with the environment. Because here we are restricted, here the convergence is related to the amount of times that we visit the state action space, and we do only one update each time. So DINA comes with the idea of planning, and it is we are having experience with the environment in the form of we accumulate this. I am at a given state, I take an action, and I have as an output a reward and the following state, right? This is if this can be thought as if we are sampling once this dynamic of the environment. So we are sampling the function that relates the state actions and the following rewards and next state. So the idea of DINA and all planning methods is that we store that experience. So we accumulate in a buffer all those experiences that we are having. And while we are interacting with the environment and getting new information, we are at the same time iterating through my experience buffer. And we are making also action value updates by replaying those experiences. So with this, we can accelerate the convergence in terms of episodes and environment simulation because we are doing a lot more updates between each step.
Okay, so thank you very much for your presentation, for your nice answers. I think there is no more questions, so maybe we can finish this last plenary lecture here. Well, I would like to remind all of you that this afternoon we have a round table, so you just have to click on the Zoom link, which is on the platform of the conference. And well, thank you everybody, and see you on next sessions this afternoon.
Thank you. Goodbye.
Goodbye, Jose Manuel. Bye, everyone.